Unit 17, pages 267 to 271. Titration of a diprotic acid. Remember, diprotic means it has two hydrogens. Diprotic acids have two protons, or two hydrogens, that will be donated as H+. When a diprotic acid reacts with base, the protons react sequentially. That means one hydrogen first and then the second hydrogen. As mentioned on page 211, the equilibrium constant for the reaction of the first proton, K1, is much larger than the constant for the second, K2. This means essentially all the first proton reacts before the second proton begins to react. The titration curve exhibits two equivalence points. The first equivalent point occurs when all of the first proton is reacted, and the second equivalence point occurs when all of the second proton has reacted. The curve below shows the titration of the diprotic acid H2SO3 with sodium hydroxide. So here is the ionization of the first hydrogen, and this would be the halfway point, and then that's where the pH equals the pK1, and then here's the first equivalence point, and that would be here where H2SO3 and hydroxide yields HSO3 negative and H2O. So only the first hydrogen transfers over to the hydroxide to give us HSO3 negative and water. Then after that one finishes transferring, then the second proton from HSO3 negative begins to transfer its hydrogen over to hydroxide, which is going to leave us with SO3 negative 2 and water again. And so here is the halfway point of the second ionization, and then here is the equivalence point of the second ionization. Example 17.87. When 45.1 milliliters of an unknown sodium hydroxide solution is titrated with a 0.0742 molar hydrochloric acid solution, and 31.5 milliliters of the hydrochloric acid solution is required to reach the equivalence point, find the concentration of the unknown sodium hydroxide solution. So here is the reaction, hydrochloric acid plus sodium hydroxide, and it's going to yield water and sodium chloride. And then I wrote what I've been given here, that for hydrochloric acid I have a volume of 31.5 milliliters and a molarity of 0.0742 molar. And then for sodium hydroxide, I have a volume of 45.1 milliliters, and I don't know the molarity. So this reaches all the way back to last semester when we learned about stoichiometry of aqueous solutions. Notice that you have molarity times liters, and molarity times liters equals moles. That's a milli, so I'm going to actually just kind of keep that, and we're going to have millimoles of HCl. When I multiply these, I get 2.3373 millimoles of hydrochloric acid. Now, I'm trying to determine the amount of sodium hydroxide, so I need to do a mole-to-mole ratio from hydrochloric acid to sodium hydroxide, and it's 1 moles of hydrochloric acid to 1 mole of sodium hydroxide, which just means we have the same amount, 2.3373. And that's going to still be, notice moles of hydrochloric acid cancel, millimoles of sodium hydroxide. Don't let the millimoles throw you off. Still moles, it's just a millimole. And finally, now that I have the moles of sodium hydroxide, moles divided by liters equals molarity. So if I take this and divide by 45.1 milliliters, notice the millis cancel, I get moles per liter, which is going to equal the molarity, which is 0.0518 molar sodium hydroxide. So this is the concentration of the sodium hydroxide that it took in order to neutralize completely this molarity of hydrochloric acid when these two volumes were added to one another. So this should take you back to the good old multiply stoic divide that I taught you a long time ago. However, if you look at the rest of these notes on page 268, you'll see a different type of equation that can also be used to solve a titration calculation. Example 17.88. We're going to use the same reaction, so I'll go ahead and write it out now. And we are told an initial concentration of 0.0518 molar sodium hydroxide, 45.1 milliliters of sodium hydroxide, and we have a molarity of 0.0742 molar hydrochloric acid. Find the pH of the mixture at these 4 points. So here, the question is, what is the initial pH? this is the point of the titration where the only thing present is the sodium hydroxide, this guy right here. So the question is, what is the pH of this? And so first, I'm just going to take the molarity, and if I take the negative log of the sodium hydroxide concentration, remember that that's also going to be the molarity of the hydroxide concentration since they are a 1-to-1 ratio here and here. So this gives me 1.29, but remember, negative log of hydroxide is a POH. However, if I want the pH, I will do 14 minus this value, and I would get a pH of 12.71. So that is what the pH is starting up here. And according to the graph, that should look like it makes sense, that it should be way up here close to 14 because here is about 1, here is about 7, and up here is about 14. So now we're at point number 2, and this is going to be where we have some base, but we've been adding some acid also. So we have mostly base and a little bit of acid, and so what would be the pH around this point right here? And they tell us that we have 10 milliliters of acid that has been added. For point 2, I have rewritten the equation, and I wrote here that we started out with 0.0518 molar sodium hydroxide and 45.1 milliliters. Here we started out with 0.0742 molar hydrochloric acid, and at point 2 we've added 10 milliliters of the acid, and so I have that information right here. So first of all, I want to know how many moles of each of these we have reacted, and so when I multiply 0.0742 times 10 milliliters, I'm going to get a value of 0.742 millimoles of hydrochloric acid. And when I multiply these two, I'm going to get 2.336 millimoles of hydroxide. Now, these are going to react on a 1-to-1 basis. So what that means is exactly 0.742 millimoles of hydrochloric acid is going to cancel out 0.742 millimoles of the hydroxide. And notice we have more hydroxide, so which we expect. There's excess base present here. So what I'm going to do is subtract the 0.742 millimoles from this hydroxide, because that's how much is going to be canceled out by the acid, and what I have left over is 1.594 millimoles of hydroxide remaining. Now I need to know this molarity so that I can get the pH, and the molarity is going to be the millimoles divided by the total volume, 10.0 milliliters plus the 45.1 milliliters. And when I do the total volume, notice all the millis cancel. When I do 159.4 divided by 55.1, I get a molarity of 0.0289 molar hydroxide. And so taking the negative log of this value gives me a POH equal to 1.5386. And then if I take 14 minus that value, then I get a pH equal to 12.461. So we started out with a pH of 12.71, and then here we're at a pH of 12.461, which makes sense. It gradually moves downwards. Now we're going to go to point number 3, which is asking what is the pH at the equivalence point. And because this is a strong acid and this is a strong base, we can automatically say that the pH is going to be equal to 7 at the equivalence point. Finally, we'll look at point 4 here where there is excess acid. And so notice we've gotten past the equivalence point and almost all of the base has reacted, and now we have an acidic pH, so an excess of acid. So here, again, sodium hydroxide, the original amount, 0.0518 molar and 45.1 milliliters, and then for hydrochloric acid, there's the molarity, and now we're dealing with 40 milliliters of acid. I want to figure out my millimoles of each of these. Millimoles of this is going to be 2.336, and here when we multiply these we get 2.968. Now notice that again these cancel out at a 1-to-1 ratio, and we have excess acid right now, so we expect there to be more of this than there is of this. So I'm going to subtract 2.336 millimoles from the acid, and what I have remaining is 0.632 millimoles of hydrochloric acid, but more importantly of hydrogen. And so now I'm going to divide it by the total volume, 40.0 milliliters plus 45.1 milliliters, and this is going to give me a molarity of 7.4266 times 10 to the negative 3, and that's the molarity of the hydrogen ion concentration. If I take the negative log of this, then I get a pH equal to 2.129 at 0.4. And of course that makes sense because we're at excess acid, so we should have a relatively low pH. So here's your note card, and it could be reversed if you're starting with the strong acid instead of the strong base. But if you're at a point of the curve way up here, then you're at the initial point and you can take the negative log of the amount of base you have. Keep in mind how many hydroxides there are. So if there's, say, calcium hydroxide has 2 hydroxides, then you would have to do that concentration times 2. And that's going to get you the POH, and then subtract from 14 to get your pH. Here is where you still have more base than you do acid. So you're going to take the moles of the base minus the moles of acid and divide by the total volume, and then that's going to get you the hydroxide concentration, and you can take the negative log of that to get the POH. And here is the equivalence point, and so it's going to be a pH of 7 because it's strong acid and strong base. And then here you have more acid than you do base, so you'll take the moles of the acid minus the moles of the base divided by the total volume, and then that's going to be the concentration of hydrogen. And so if you take the negative log of that, you would actually have the pH at this point. Remember up here that you have to subtract by 14 to get the pH for both of those points.